Good afternoon, ladies and gentlemen, and welcome to the SAIEE Rotating Machine Sections webinar. We will be discussing today rotating electrical machine installation, the history, trends, and developments. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the Rotating Machine section playlist. This channel is updated regularly, so ensure you check back as often as possible for new uploads. In the chat function, you'll see, in the chat box, you will see a link to subscribe to the SAIEE TV channel. Please do, it is for free. A certificate of attendance will be issued a few weeks after this webinar once we have received the CPD validation number from EXA. I'd like to introduce you now to the host for this evening, is Mr. Jabulani Bembe. Jabulani completed his BEng and MEng in electrical engineering from the University of Johannesburg. He also completed the BTech degree from Bold Triangle Technikon. He holds the government certificate of competency in electrical and mechanical engineering. He has more than 20 years experience working in electrical machinery repair and research industry. He currently works for the South African Power Utility Eskom as a researcher specializing in asset conditioning monitoring. He is a member of the Institute of Engineering Council of South Africa and the South African Institute of Electrical Engineers and the Institute for Mechanical and Electrical Engineering Council of South Africa, IMEXA. He is also the chairman of the SA Rotating Machine section. Over to you, Jabulani.
Thank you, Mix, and thank you very much for that introduction. And I'm now going to introduce my colleague, that is Rob Malai, who's going to give us a very interesting topic before the end of the year, and we really appreciate what Rob has done for us so far in terms of this presentation. And we're looking forward to his presentation as well. And I'm also very interested in finding out what the trend is, because one of the things that we were discussing earlier is about what's the impact of climate change in terms of the design of the machine today, and what is the machine of the future would look like. And then I think Rob will be answering those questions, and we're looking forward to that. So in terms of Rob and who he is and where he comes from, Rob graduated in electrical engineering from the University of Witwatersrand in 1993, where he developed a passion for electrical machines that remains with him until today. Rob has presented courses and authored or co-authored papers and articles both nationally and internationally. He's a member of the SAIEE, South African Institute of Electrical Engineers, a past chairperson of its rotating machine section, and the current chair of SAIEE's Rotating Machines Technical Liaison Committee, TC2, and the IEC. Rob has also chaired the Electrical and Allied Industries Association of South Africa, South African SAIEE Employer Organization. Is a member of West Universities and Northwest University Industrial Advisory Body. Rob, thank you very much. We're looking forward to your presentation. Up to you.
Thank you, Jabu. Assuming you can hear me.
Yes, I can hear you, Rob.
That's right. Okay. Good afternoon, everybody. First of all, I owe my apologies to the rotating machine section for not attending the meeting this afternoon, but I had urgent work matters this morning that left me last minute planning to have to do this afternoon. So this topic is actually, it was done in a bit of a rush. It was actually planned to be a topic of discussion for next year. And when we were left without a presentation for today, which wasn't a big problem. I mean, we don't have to have a presentation. I thought, no, let me push my procrastination ability and do something. So I've said trends, history, trends and developments. you have to look at the history and trends to understand the final question that's asked or the observations. And the final question and observation is very simple. It's just that is 6.6 kV insulation on stators of modern stators, is it too thin? Is it a problem? And it's not. It might sound like it's a controversial topic, but you'll see that it isn't actually. It's just it's pure technical interest material. And I realized that you have to do a lot of introduction. That's why I said in the abstract that this is quite an educational presentation. And most of it is actually introduction until it gets to about the last third. So let's get on. Just the background I've mentioned, some theory and technical details, and we need to look at the components of a rotating machine winding before we can conclude or analyze insulation. That then, in that respect, there's stator and rotor windings. Obviously, in squirrel cage induction motors, without insulated cages, then the insulation doesn't apply. But rotor insulation is actually a lot more common than we think. It's on wound field in synchronous motors, as well as wound rotor induction motors, and for that matter, DC armatures. Then we delve into it a little bit deeper in terms of main wall insulation, turn insulation, and strand insulation. And this presentation is specifically about main wall insulation of medium voltage. I often refer to it as high voltage in the presentation because the medium and high voltage is sort of interchanged between Europe and the US, between machines and switchgear and transformers. So I'm talking about 3, 3, 6, 6, and 11 kV. History, I actually realized about half an hour ago that I left out a slide on this. All it is it's a graph of how the main insulation, the average main insulation has decreased in thickness over the years. So that's what it shows. And then we look at I work in the repair industry, and we've noticed that we see a higher ratio of 6.6 kV stator failures from most OEMs. In fact, if not all, depending on how well they are represented in Africa and South Africa. And the failures are over a particular period, like from about 2 to 5 years, so outside the warranty period, but way too early to be considered normal operation. And then I asked the question, why so many 6.6 kV failures? And then I say, well, why is this not picked up by the testing requirements? And I'm talking about the not routine tests, but type tests, and specifically the thermal cycling test at elevated voltage. And then are the testing requirements adequate? And there's just a couple of aspects, and it's only for discussion. Actually, there's no acknowledgements this time because this is just pure technical content and sharing information and asking a question. There's no advertising. There's no anything I could acknowledge. My employers and customers and colleagues over the years that sort of have led me to asking this question, whether it's right or wrong. So the objective, of course, of main insulation is to prevent failures. Like this is a 6.6 kV stator that ironically didn't fail due to insulation failure. It failed due to a switching surge. But if you look carefully at this, we're talking
Rob, can you hear us?
Rob, hello. Somehow we can't hear you. We can see the action, but we can't really hear you.
Rob?
I think we've lost Rob. The Minx.
Yeah. Just hold on a sec.
Hello, Rob. Is there a way you can give him a call, Minx?
I've asked Joanne to do that in the chat. I don't have his number. Rob, can you hear us? I'm just going to make myself presenter here. Ladies and gentlemen, sorry for this. We've got a gremlin in the area there. Let's just try and get hold of Rob, and then we'll be back with you. Rob, can you hear us?
Yes, I can. Can you hear me?
Now, we lost you totally in your presentation. You couldn't hear us. So if you can just please go back, I'll just make you presenter again, so you can just share your screen with us where you were now. Maybe just backtrack a bit. My apologies.
Okay.
Rob, you there?
The video. Can you hear me?
Yes, we can hear you now, but yeah, just go a bit back. We lost you quite.
Yeah, we lost you. Yeah, we lost you when you started playing the video. So perhaps don't play the video. Maybe just do a rundown or describe the video. My apologies.
Okay. This is a Stator 11 kV Stator coil undergoing a high voltage. It should have been a destructive high voltage test. It was at 60 kV. It took the full 60 kV for the full 3 minutes. And in the video, you see a lot of tracking on the overhang and no failure in the slot. So the point I was making is that you have a very high electric field stress inside the slot, but yet that doesn't fail, and you get arcing, tracking and that on the overhang. Okay, can everybody see? Can you see this next slide?
Yes, you can see it.
Okay. So I then spoke about the difference between low voltage and high voltage. You can see a high voltage half coil is on the bottom right. Low voltage is in the center. The principles are the same. You have an overhang portion, and then you have a slot portion of the coil. You have turns, and you have main insulation. Low voltage is quite particular in that it usually has the main insulation being just a slot liner. So the slot line is inserted in the slot first, and then the individual strands are inserted through the slot lip, the slot opening, and then closed with a wedge. So it's quite a different design, but the principles are the same. Again, I mentioned the presentation is about mainly about high voltage main insulation, but I just wanted to keep the low voltage in there, and specifically rotors as well, because the whole point of the presentation is that the primary aspect of insulation to consider is not just your dielectric stress, your kilovolts per millimeter. It's also mechanical issues. And so I spoke here on the left about your main stresses in an electrical machine: thermal, electrical, ambient, and mechanical. And the stress that I'm going to concentrate on is actually thermomechanical. It's the mechanical stresses that occur due to differential expansion and contraction in a stator, due to the different heating of the copper versus the core. And then just as important is the electrical stress, and you'll see that towards the end. All the stresses act together, so the point is one has to consider all the stresses in an electrical machine in terms of determining the thickness of the insulation and other parameters. Again, I won't go into detail here. You've got this sort of fine goes in a bit closer to your stresses. So you can see under thermal, there's thermal cycling, and then mechanical, there's coil movement. So in any electrical machine, you're going to have thermal cycling and coil movement. It'll vary. Some motors, like for example, petrochemical motors, Sasol, will be designed to switch on and run continuously for 4 years. Others stop and start every hour. There, the thermal cycling is what this presentation is about, as well as, and you'll see that point is that it does still depend on your voltage stress across the insulation. So if you put X amount of stress, mechanical stress, on insulation that is sitting at 5 kV per millimeter, and the same amount of stress on insulation that is sitting at 1 kV per millimeter, you're obviously going to get a different time to failure. Your stator electrical stresses are basically about kilovolts per millimeter. In other words, what is your electric field at various points in your insulation? So you can have an electric field of 10 kV per millimeter in insulation and it won't break down. But if you have 10 kV per millimeter in air, it will break down. And depending on what insulation is involved and what the electric stresses are, you will or won't have both partial discharge, that's breakdown in air, or electrical breakdown, but that does not short circuit the entire insulation system. And in any medium voltage machine, you are going to have these stresses, you are going to have the failure mechanisms, so it's important to consider them. And in the proposal that I make, I believe that dielectric stresses are still very important because they involve 6.6 kV machines. But you'll also see that mechanical stresses are often the key parameter to consider. So stator mechanical stresses, you get typical stator mechanical stresses. They exist on all machines, on whether they're 3.3, 6.6 or 11 kV. But the mechanical stress that I'm concentrating on, as I've said, is the thermal cycling stress. Rotor stresses, the same thing. The rotor spins, so you get a lot of different stresses that you're not going to get in the stator, particularly centrifugal. So you can have, but you'll see that in general on rotors, even the biggest rotors, like I've got an example of a 120 megawatt, 3000 RPM rotor, the voltage is below 750 volts, yet you have to have very thick insulation to withstand the mechanical stresses, and not just the centrifugal. Okay, so we've got our components. High voltage on the left is the core. Then you've got the overhang section. If you look in the middle, you can see a grayish layer underneath the white layer. That is your semiconductive stress grading. Okay, and then the overhang of a low voltage machine, very similar. Your slot portion and your overhang portion. Obviously, you don't have any of the the AntiCorona stress grading components that you need in a high voltage machine. And this is your a picture showing a partially wound high voltage stator coil. So the black tape is your semiconductive stress AntiCorona layer. It goes in the slot and extends a little bit out of the slot. The gray portion is semiconductive stress grading. So it's almost an electrostatic component. And all of these are important in an insulation system. But again, we're concentrating on the main insulation. And I've introduced this so that you get an idea of the extreme high stress that exists in the slot portion when we look at the stress grading, at the reason for the stress grading and correctly functioning stress grading and not non-functioning stress grading. So this slide shows the left-hand side is the end of a core. The center is a stator conductor. It's represented as one conductor, and then the lines that emanate from that central point are your electric field lines. So the one closest to the core is 0 kV, and then they jump up at approximately 1 kV per line. And you can see that the lighter shade, the cylindrical. Let me just put I'm just nervous to use my pointer because that's what might have gone. Can you see my pointer?
Yes, we can. Thank you.
Okay. So this is the stress grading. Okay. So if the stress grading doesn't work, you've got air here, and you've got a very high electric field in air, and that's enough to cause ionization and glow discharge and all sorts of things that would damage the insulation over time. So that is this is the purpose. The stress grading is to then grade these voltage lines out so that you spread the voltage in air. So it does nothing to the electric field inside the slot. It stays just as high. But look how high that electric field is, even with or without decent stress grading. So you would have gradual wear occurring due to the corona discharge on the overhang, but you still have no failure inside the slot. And here you can see, so it's a tremendously high electric field, and it's why the main insulation thickness is so important on these machines. Okay, this is actually not. This was lower than.
Rob has disappeared again. Hello, Rob. Can you hear us?
I see Rob is having gremlins in the issue there.
Yes.
Yeah, he's gone offline. So attendees, I'm sorry, please bear with us while we get Rob back on.
Places a lot of stress on the insulation over time.
Okay. Rob, sorry, you went offline there for a second. If you can just backtrack slightly. But to 20 seconds.
One slide or just on the same slide?
The same slide, yes. Thank you.
Okay, this just shows a low voltage stator failure. It shows how thin the main insulation is, but for this voltage, that thickness would be ample to run for 10 to 20 years, provided there's no mechanical stress on the insulation. But if you can imagine, if this conductor moved in and out of here, or there was a force on it that put shear stress on the insulation, it would fail quite quickly. So then this is an example of a high voltage, and very importantly, it's the overhang. Hey? It's not the slot portion. So you can have these imperfections. This doesn't mean it's a terrible winding or anything, but these are voids that you get from delamination. Now these would discharge, even though the main insulation doesn't discharge. So, but you can just see that this is a 6.6 kV machine. Now, because it's the overhang, the insulation looks a lot thicker than the samples that you'll see later that are taken from the slot. Okay, rotor insulation. And now this is why I just want to show this. The slide on the right is about probably about a 20 megawatt salient pole synchronous machine. The voltage on the field probably about 250, 300 volts. So it has very thin insulation, but it's the failure here wasn't electrical, not even mechanical. Actually, it was due to dust, gas, sulfur in the gas, sulfur gas in the air in the plant, eating away at the brazing. But you can see here the insulation between turns here would be about less than 1 millimeter, and the main insulation would protect the winding from the core. But the main insulation would be very thick, much thicker than the inter-turn insulation, probably of the order of 2 millimeters, let's say. But for that voltage, it's actually overkill. And the reason it's overkill is for mechanical considerations. In the center is a salient pole synchronous machine. You can see V blocks in here. They hold the coil in due to the tangential component of centrifugal force. So even though the voltage is low, you have to consider very thick insulation. And the slide on the photo on the left shows that very clearly. The inter-turn insulation you can hardly see, yet the insulation that insulates the whole coil from the rotor body is very, very thick for mechanical considerations. And this is a failed field winding. This started off as an inter-turn failure, so the turn-to-turn insulation failed, but probably because of stress of the V block pressing against the insulation, and it eventually failed with a failure to earth. Otherwise, it would have been very difficult to pick up. This is another rotor. This is now wound with rectangular enamel wire. You can't see it that clearly, but if you look carefully here, you'll see it's got insulation between layers. And I've included this to show and give an idea of the sizes involved. That's in millimeters. So you can see that insulating strip is about 1 millimeter thick. And the nameplate of that machine, just to give you an idea, quite an old machine, a 3.7 MVA. But what's interesting about it is look at that excitation voltage. So that coil only sits at 55 volts, and yet remember that this is the turn insulation. The flanges, so the main insulators from the pole body, are much thicker. And again, there mechanical implications totally override electrical considerations. So now we look at a typical stator. Two typical stator coils, samples from coils. This is it's actually a resin rich. It's not a VPR bar. You can see here it's 11 kV. I've put a ruler there to show you the clearances, and you'll see the relevance of this later. So that's probably about 3 millimeters. It's a Rubel bar, so this is a single turn. So, and then on our right is a VPR stator sample. Thank you to Mario Cases for this one. And you can see that the turn-to-turn insulation is very thin. And again here, because it's a VPR coil, it doesn't have the accurate outer dimensions. So it's not formed before insertion into the stator. Again, you can see the dimensions here. I've zoomed in quite a bit because it's a smaller coil. Then this is a sample of another sample of also a resin-rich coil, and this is quite interesting in that it includes turn insulation. So most modern machines use the strand insulation as the turn insulation. They don't add any insulation between turns. The Americans still like it, but it's not commonly used today. So there again, you can see roughly the same sort of 3 millimeters on this 11 kV bar. This is a very interesting sample cross section. I keep it in my office. It's actually of one of the Kelvin 60 megawatt machines, and it was a failure brought on by a fault. It's 11 kV. It's 11 kV, about 1968 vintage. It's got higher than 2.5 kV per millimeter dielectric stress, and that's how long it lasted. Very interesting for the specialists here. It's a 3-turn Rubel bar, so it's quite rare. When we went to probably one of the best Rubel bar manufacturers in the world, and we gave them this cross section, they said, sorry, they can't replicate they can't manufacture the replacement bars with the same insulation thickness to their standard, meaning that the Swiss workmanship and standards and everything else from 1968 were better than what we are able to manage today, and especially since these machines have been operated and to some extent operated quite let's say ruggedly. It's actually a testament to the workmanship and materials from those days. And then we look at that's a reasonably modern 6.6 kV overhang sample. Again, here you can see the interturn insulation. This hasn't been polished like the other examples, so it looks like it's got no interturn insulation. You can see again, being from the overhang, it's got very puffy edges, but you can almost see the number of layers and guess and gather about the main insulation thickness. Most of the insulation of the main insulation of modern machines, even machines up to 30, 40 years ago, is mainly mica, backed by either a polyester backing or a glass fabric backing. This is the film backing. Okay, then that's the same sample of earlier, just showing you it from the side. If you look at how accurate the external dimensions of this coil section are, this is a resin-rich sample, meaning it is pre-formed before it goes into the stator, and that's quite different from most modern machines, which are of the global VPR type. And this is just to keep the low voltage relevance. It's mainly all about enameled wire and slot liners. Enameled wire all depends on, it's based on different grades. The grades basically link to the thickness of the main insulation, and the second parameter is temperature. Here's a low voltage machine, partly wound. Sometimes I think it's amazing that they actually completely wound these things when they look like this. Your different slot designs, most of them are this type on the left here. So you have your slot line around outside and your round wire and your wedge that fits in at the top. But again, the principles are the same. The machines are much smaller, the voltages are much lower. So with smaller machines, there's less relevance to differential thermal expansion and things like that. With electric vehicles, things are getting quite a bit more complicated. There's now hollow conductors. They are using a lot of the techniques reserved historically for larger machines now in smaller machines for electric vehicles, like rectangular conductors, form wound windings, and the like. So it'll be interesting to see how that develops. But the voltages are still low, although climbing. They've gone from sort of the 48 volts to 400 volts, and now to 800 volts in the highest voltage rating electric vehicles. I mentioned the next important parameter about round enameled wire is the temperature, and these are the materials used for the different temperature grades. I'm not going to go into detail about that, but you basically get your 180 degree, 200 degree, 220 and 240, and they each use a different type of enamel. It doesn't always have to be the same, obviously. Different manufacturers use different types. And your average diametral thickness of the different grades are 0.01 millimeters, 0.017, 0.024. So it's on each, if you look at manufacturer samples, they vary. I mean, they give a minimum and a maximum. So again, this presentation is about high voltage stators. And these are your typical components, your slot component, your overhang component. This is a typical slot with your top and bottom sections. You get various different types. Here's a partly wound stator. The coils are fitted in the slots, and you can see here that these coils haven't had the wedges fitted. Those are your wedges there. Again, I mentioned that rotors, voltage applies to rotors in terms of wound rotor induction motors, DC armatures, and wound field synchronous machines. I've already shown you examples of some examples. I've got more to follow of wound field synchronous machines. But here is a wound rotor induction motor rotor, and you can see the slot liner over here. So very similar to low voltage. They have a certain amount of tape on the conductor, and then they use either one or more slot liners. Partly wound concentric stator, quite rare. You can see the open slots there that haven't been wound yet, and these coils have been fitted with wedges added. Another example of a wound field using rectangular conductor. Again here, notice the thickness of the insulator separating the whole field, and this is actually quite a thin design. It's an alternator, which they tend to push limits on, even historically. Low voltage, I mentioned there, that same slide. You can see that there's the slot liner. You can have more than one slot liner. But in a low voltage machine, your strand insulation actually plays a fairly significant role in terms of the overall insulation. You can get low voltage. This stator is less than 3.5 kV, and it's rated at 20 megawatts. So you can have low voltage at very, very high powers as well. So there you have to consider mechanical stresses, even in a stator. And low voltage doesn't have to only be mush wound with round copper. It can also be form wound. This is a 120 megawatt rotor. Rotor voltage less than 750 volts, but massive insulation considerations to be taken into account for the mechanical considerations. I mean, if you base the insulation thickness on the voltage, it would be sort of 1 millimeter thick, and yet it's way more than that for mechanical considerations. Here's a close-up view. This is a 26 megawatt cylindrical rotor machine. You can see this is the slot insulation, and you can see how it's worn here. It's actually worn due to abrasion from contamination, but you can get an idea. And there's your turn insulation. So again here, big machine, low voltage, but you still require substantial insulation. So now we get on to back to the same some slides, but we look at the difference between main wall, turn, and strand insulation. Your main wall insulation is here. Your turn insulation is this insulation here, or on modern machines, it's the insulation between these strands here. So in other words, they don't use dedicated strand insulation like this, for example. They rely on the strand insulation to be the turn insulation. And then that Rubel transposed single turn design that we saw there of 11 kV. So this is your strand insulation normally takes very low voltages except under transient conditions, but it's still important to test it. The average repairer, even OEM, doesn't do testing of their conductor. They rely on the suppliers, but this was some testing that was done a couple of years ago where you dip the conductor in and you can see where it fails. You have different types of taping, butt lap, half lap, etc. and this shows Kapton covered wire. So strand insulation is very important, but this, as I mentioned, the presentation is concentrating on a specific aspect of insulation, and that's the main insulation, and that's this insulation over here. So let's take an example. There's two types of stress that are going to occur: thermal expansion stress. The one is the cross-sectional stress. So in other words, the copper will expand in the height and in the width. The width is obviously very low, so we don't need to worry about that. Let's take an example of a 100mm deep coil. We assume it's all copper, and we work, I think I worked on a 60-degree delta T. The expansion in the height of the slot will be 0.1 millimeters. So it's very little. It won't exert a major stress on the insulation at all. But if we take the longitudinal expansion and we consider a 1 meter long core, the expansion will be 1 millimeter in the length of the slot. Now imagine that 1 millimeter over the thickness of the main insulation, which you'll see now. 3.3 kV is typically between 0.9 and 1.2 millimeters per side, 6.6 between 1.2 and 1.6, 11 kV between 2.3 and 2.6. This varies depending on certain things, like I said, resin rich versus global VPR, but I've tried to look at a decent average. So now let's look at the average dielectric stress on a 3.3 kV machine. It's 1.9 kV per millimeter, which is low. The normal range is between 2 and 3. A lot of OEMs push a lot higher than 3 today. 6.6 kV, 2.7 kV per millimeter. So it's medium to high. And 11 kV is 2.65. So it's also round about the same as the 6.6 kV. But the reason the 11 kV is because it's based on electrical limits, same as the 6.6. The 3.3 is a lot lower because if you based it on the electrical stress, it would be so thin that it would experience mechanical failures. So that's why 3.3 is a lot lower, and that's quite relevant to this to the question posed in this presentation. So now let's look at the mechanical expansion stress on three example stator half coils of 1 meter in length. If we assume 0.5 millimeter expansion, so there I've taken that 1 millimeter and I've assumed that the coil expands from the center of the core, which may not necessarily be true, by the way. It often expands from either end. Then the shear stress is 0.5 millimeter over 1 millimeter of insulation. So it's quite substantial. 6.6 kV, 0.5 millimeter over 1.4 millimeters. So it's 36%. It's sort of medium stress. And 11 kV is very low. It's 21%, 0.5 millimeter over 2.4 millimeters. So imagine that coil trying to shear the insulation. In one case, it tries to shear 1 millimeter. The other one, it tries to shear 1.4, and the other one, it tries to shear 2.4. So what we found is, as I mentioned, on 6.6 kV stators from several OEMs, good OEMs that don't experience failures often. And these were all in the range of 2 to sort of 5 years. And in all those cases, we found that the 6.6 kV insulation was in this region here. And we proposed in many cases to actually decrease the copper size and increase the main insulation thickness. And we don't find the same in 3.3, and we don't find the same in 11 kV. So the question asked why, and most of these, sorry, were on machines that had quite a lot of thermal cycling. So the question asked is, you know, these insulation systems are tested, and this video, which I won't play, shows that same coil after the 3-minute 60 kV test failing at 76 kV after about, I can't remember, but just less than a minute. So I mean, it should have failed way before that. And the interesting part about the video, which will be circulated and you can actually watch it in the presentation, is that it still does not fail in the slot. Despite that massive electric stress in the slot, it doesn't fail there. It fails on the overhang. So it tracks the tracking eventually just causes the overhang to fail. And so if we look at the test requirements, there's two types of tests: routine tests and type tests. Routine testing just usually is your worst test is actually a high voltage test. It doesn't check any mechanical integrity or thermal. It's just a voltage test. But type testing should. Type testing, the most important type test, in my opinion, is the thermal cycling test at elevated voltage. So why would it not be able to detect this failure mechanism on in these with this thinner insulation? And after a while, I looked at the way the testing is done. I think a lot of you know it. It's using a format. So it's a simulated stator. So it's got, see here on your right, you've got coils. The overhang is usually the full size, but the core is often a shorter version of the coil. You would have this example here in our video is actually a format, but it's a full size format. So we actually replicated the full stator core length. So here we look at the format, and there should be something very interesting that you notice about this. Is how representative is it? The coil length, it's shorter, typically. The core length is also shorter. Okay, and the core versus the coil temperature. Now, in a real machine, when that machine starts up, you get a very different temperature between the stator coil and the core. In these thermal endurance tests, everything's heated up together. I think most of them use the steel portions, the simulated slot portions, to actually heat up the coil. So your core does not heat up and expand in the same fashion as in the test as it does in the real machine. And to show you a few more examples, there's another format. These I just picked up off the internet, and this one in particular, short lengths and very much that I think in most of them, and there might be some specialists here that can comment, that the core, so the test core is heated up directly. Meanwhile, in reality, the copper heats up the core, and there's substantial difference in expansion and contraction. So a long way of getting about it, because I tried to introduce the topic and to try and introduce stator insulation in 45 minutes is not easy, but I hope I've given some idea, and just to give you a feel of the thicknesses of the insulation. And the question is just, you know, this high ratio of failures, where does it come from, and why just on 6.6 kV? And is the fact that 6.6 kV insulation is based on the electrical stress maybe too far reach? Should it not have some amount of mechanical allowance, as has been the case in the past? Back when I was at ABB many years ago, the limit we used for 6.6 kV was 1.6 millimeters. And then the second part is related to the type test, the thermal cycling elevated voltage endurance test. Is that really an indicative or representative test of real stators, especially ones with long core lengths? So we get a lot of stators, 6.6 kV stators with thin insulation that run for a decade, even 20 years. They typically have short core lengths, or they don't thermally cycle much in that. So it's not a problem. It's just an observation, and the question is posed, and it's mainly for discussion. So thank you very much. Sorry about the issues with the web or communication. My apologies.
Thank you, Rob, for the presentation. I think it was well done. Yeah, I wish we could go the whole day, Rob, because the amount of information that you have is taking us, all of us, way back, and it's very fundamental. And we thank you very much for your contribution as well. And we're looking forward to you giving us more information in the future and sharing knowledge with us, Rob. Thank you very much for the time that you've put into this. Okay, let's go to the audience and see if there's any question. It means I can't see very well this side, but let's just find out if you can see any question from your side, Joanne.
Jabulani, we don't. We encourage the attendees to ask questions in the questions panel, which is located on the right-hand side of your screen, which you can answer now.
Yes,
We've got
I see this. Okay, go ahead, Ms. Van.
Okay, thanks. We've got one from Althea Feldman who says, just well done.
Okay, thank you. So Rob, while the audience maybe is trying to put the questions together, my question is on cyclic and mechanical stress on these 6.6 motors. How much of failure does that contribute to the overall condition of the generator, the cyclic, especially now, because I know in the past we used to have the luxury of running the machines, you know, for a long period of time, but now because of certain things that we experience even in the ESCOM, you have to run the machines maybe at a certain period of the day and then you shut them off and then you run them again. So how much of cyclic effect does the environment have on the 6.6 machines?
Okay, again, it would depend on the type of machine, the type of stator, the sort of the nature of the thermal cycling, but in general, there's a substantial implication. It can make the difference between a machine lasting 15 years and lasting 5 years. But I know EPRI's done a study on it, and I think one of their studies is actually public knowledge, public IP, publicly available, and when it comes to your size machines, the thermal cycling on the stator is actually quite it's not as severe because you're using preformed bars. So this presentation has been about VPR machines where the coils are glued into the slots. So the insulation is effectively a glue sandwich between the copper and the slot wall. So if the coil expands, it puts that shear stress on the insulation. Whereas in a resin-rich machine or an individually VPR machine like your big generators and that, the bars are free to slide in the slot. So the stress is not nearly as much. I do know that in the past, several OEMs started getting bigger and bigger with global VPR machines. So they went up into I think the 250, sort of 300 megawatt region. And I'm sure there's others that can comment, but the main failure mechanism on those global VPR machines was related to the differential expansion of the stator copper and the slot wall and the gradual deterioration that it caused to the insulation. So much so that later on, at least one of the OEMs worked on a slip plane. In other words, a global VPR machine, but with an intentionally introduced slip plane for the coils to expand and contract longitudinally. But yeah, it's a big issue, and I'm sure you know. I mean, it's part of the C-grade discussions. It's all over the place. I don't know if that answers your question.
Rob. Definitely, Rob. I think there's also a similar question. Rob, can you give a breakdown of what would be the most important, most important contribution of factors on ESCOM thermal power generator rotors? I think you've mentioned that. Maybe do you have anything to add to that?
Sure. I'm not I'm not an expert on big rotors, but I mean the principles are the same. I do know that arcing, CRR arcing to wedges, or in terms of rotor arcing, has been a problem over the years. And interestingly enough, I read this recently, that there is a 10 times higher incidence of CRR arcing in Australia and New Zealand for some strange reason compared to the US. And then the rest of the document went on to identify the reasons for the CRR arcing, and most of it was incorrect operation. So I think that you could probably comment better than me. Faults are very relevant. I would say earth faults. But to me, the most important parameter is to, in terms of preventing failures, is to use a reliable, proven design, and to operate it correctly. I mean, on thermal, in the thermal, well, at least coal stations, your cycling is limited by your coal side, your boiler side. So the thermal cycling on the electrical machine is not as bad, but with gas turbines and things like that, it gets a lot more. And yeah, the EPRI study, I think, is concentrated on hydro machines, which can cycle significantly without any problem related to the water side.
Thanks, Rob. Yeah, you're quite right. We've had quite a number of such cyclic related problems in the utility, and yeah, it was over the years that thing was then discovered. But before then, machines were running normally in terms of base load. But over the years, when we started cycling machines because of whatever problems, when you started seeing these symptoms of the copper overgrowing, and also the actual, because the copper sometimes tend to expand at different expansion lengths, and then the OEMs that we've worked with in the past, they've then introduced slip lanes, that you've just mentioned, and it kind of avoided some of the issues that we face. But it is a problem, and it's something that I think the utility is working on with the OEMs as well to make sure that we avoid it in the future. In terms of the faults on the CRRs, yeah, that is, at times people do motor the generator, and then we have all sorts of problems. But yeah, that is things that we live with sometimes as people. Okay, any other question maybe from the audience? That me taking over the discussion. I think you've got Rob at your disposal, and we're very fortunate to have Rob giving us this information. Manuel says thank you. Rob, he says thanks for the presentation.
Thank you.
We've got a question here from Althea Feldman, who's a two-part question. She says, she asks, do you think end users should request a certain insulation level for 6.6 kV motors? Is this possible to dictate kV and millimeters? And the second part is, would brazing assist the mechanical stresses for this type of phenomena, or not really?
Sorry, would brazing assist?
Yes, would brazing assist the mechanical stresses for this type of phenomena?
Okay, the first question, I actually went on a search about this, and the best guide is an EPRI guide on repair of a range of nuclear motors. It's a very good guide, and it's also publicly available. I'll actually send it to you, Althea. And in it, they actually give guidelines to the recommended range of dielectric stress, and it's between 2 and 3 kV per millimeter. So it doesn't address the specific aspects of the range that I'm talking about. And I talk 6.6, but I mean it could just as well be 4.16 kV in the US or 7.2 kV in Europe. I think it's just that range. So they definitely do define it, and very, very interestingly, they also point out the fact that the dielectric stress on low voltage machines is hardly of any influence because mechanical issues play a far more important role. So it's very, very clearly defined by them and the limits given. In terms of enforcing it on an OEM, it's very difficult because the big advantage of thinner main insulation is not so much the fact that you can make the copper bigger or greater in cross-sectional area and get lower losses. It's the fact that the thinner insulation allows a greater heat transfer through it. So you get a double benefit. So an OEM, if you ask them, no, we need this insulation thickness on these machines, then they'll say to you, well, then we can no longer make you a, I don't know, 2.7 megawatt, 6.6 kV in a machine in a 500 frame size. So it's quite a, and the argument will also be, well, we've made hundreds or thousands of 6.6 kV machines that don't have problems, and they're quite right. If the machine doesn't thermally cycle, it's got a short core, you don't have problems. So but it's just that we've picked up a definite, and it's not just here in my previous things. And I'll tell you one thing: we have had an OEM accept in writing to our proposal to reduce the copper size and increase the insulation size on a rewind. So they do sort of agree that it's an issue, that it's there as a potential issue, but only on certain machines. And there's always the harsh African conditions to consider as well. About the brazing, I'll have to ask you that question, or we discuss that question later, because I don't understand it completely. I apologize. I know it's something very obvious and clear, but I'm just having a blank at the moment.
Thanks, Rob. So just another question, Rob. In terms of the copper composite or composition, what is the composition most of the time of the copper, as in a chemical composition?
I think most copper today that stators are made of is oxygen-free copper or electrolytic tough pitched copper. So it's oxygen-free copper is 99.8% copper. I don't think there's any difference. Some field windings use exotic sort of silver content and whatever, but for mechanical reasons, to prevent creep and stuff like that. There's quite a strong movement today towards 3D manufactured copper windings or additively manufactured. And the problem there is that the conductivity is not up at the levels that they require it, but it's improving very, very quickly, very quickly. I mean, I remember seeing sort of 70% 2 years ago, and they're already up over 90%. That's going to be quite interesting. But yeah, most windings, rotor windings are different. Your dampers often use brass. Rotor bars often use a brass alloy to get higher resistance. But stators are normally oxygen-free copper or electrolytic tough pitch copper. Mostly oxygen-free copper, because it's most copper drawn today is manufactured by that continuous extrusion process, and that basically requires oxygen-free copper. Hello?
Thank you.
Thanks, Rob. Any question on your side there, Mings, Joanne?
No, nothing. I just didn't say that's all the questions we have. Oh, sorry, there's a last one.
Hello?
Our last question for tonight then is from Johnny Nunes, who's asking, would improving the cooling around the overhang region of the stator winding not reduce the thermal expansion?
Well, it may, but I don't think by much, because you're still looking at the section in the slot. That's the section that matters in terms of the thermal expansion, and you might get sort of a small benefit of a little bit more heat being transferred from the slot coil section into the overhang. But I think it would be that if you did a study, you'd prove that it's of sort of minimal, if not, well, it will be almost like negligible.
Thank you, Rob. I see Jabulani. Oh, there he is. Over to you, Jabu. Yes.
Yes. Okay. Thank you. Thank you very much, Rob, for your for that presentation. I think, as usual, we gained a lot, and we're looking forward to something like that in the future. And also, just want to encourage the attendees today to check out our the SAIEE website and look at the RMS, what we're up to. And there's obviously more coming next year. And please have a look. And if you've got any suggestions as well, you're more than welcome to drop them with Joanne, and then we'll see how we can even better this in the next coming year. But nevertheless, thank you very much. If there's no other comment, thank you very much, and see you next time.
Thank you. Thank you, Mings. Thanks, Jabu.
Thank you, Jabu. Thank you to the attendees for joining us today. Please watch out your email box. Within the next few weeks, you'll receive your CPD or the attendance certificate with the CPD validation number. Rob, thank you for availing yourself for this presentation today for the RMS section. Jabulani, thank you for taking the time and hosting this event. Ladies and gentlemen, just lastly, in the chat function, you'll see the links to the SAIEE CPD calendar. Please have a look at upcoming there. You might be able to clinch the deal and get in the last CPD credits you need for this year. Also, subscribe to the SAIEE TV channel. It is for free. It's on YouTube. The link is in the box. And if you're not a member of the SAIEE and you want to start reaping the benefits, please click on that link and check what we offer. I thank you very much for joining us tonight. Have a wonderful evening. And if we don't speak again, and if we don't meet again online, have a Merry Christmas. I know you're all going to shoot me, but have a Merry Christmas. Good night and goodbye.
Thank you. Thank you. Bye. Bye.